Hello and welcome to Mike's Basement. I know that I said that I would never ever do a flat earth video again. Well, perhaps not in that exact wording, but I did say that I was sort of done doing flat earth videos because the arguments always tend to be the same. The same stupid memes, the same stupid arguments, the same stupid sayings about flat earth makes it really uninteresting to really discuss any further. I think that at least here on the Danish sites that people are just repeating themselves. But then something happens. Something happened. And I saw a video where I just couldn't keep myself from wanting to get into that thing again, that area. So let's watch the first part of that video.
A famous astrophysicist unwittingly walks into an interview with a flat earther and rage quits within an hour. Some of my favorite moments you're about to see from this interview include, number 1, her repeated use of the word interesting when faced with gaping holes in the heliocentric model.
It is an interesting question, yes. You know, if it's not a fake news, then you have to say, okay, interesting.
Number 2, her suggestion that if real-life observations aren't matching the heliocentric model, then, quote, the model is wrong.
You shouldn't be able to see the moon from both places, so there's a problem somewhere.
So probably model is wrong, I'd say.
Number 3, her multiple references to Hollywood fiction space movies to bolster her arguments when faced with a lack of real-world evidence for her claims.
Surely we'd have seen that being tested on Earth, or we'd see things now.
It's jumping, yes. Did you see the movie of First Man, it's called? How he practiced, I mean, in the movie. And they are like not homogeneously distributed all over. There are like packs of them. Like in that, remember the movie Gravity again?
And number 4, finally, the incredible rage quit at the end where, upon losing epically to a flat earther, she thuggishly uses her credentials in astrophysics as an appeal to authority club to bash him over the head with.
Different tests of the same thing coming with the same results. That's highly scientific.
I should have asked your credentials before I talked to you. I'm sorry.
Alright, so now we have the scene set. Let's get going. The first thing I want to point out is that this person, in my opinion, doesn't really get by his interview with that good of a start. Just listen to this.
Interview her, but how? I thought about it and I created an alias. David Howard from Oxford University Media Society.
Just think about that. He creates an alias in order to get an experiment with a non-flat earther instead of just being upright up front. And he's just, I think it's faked. He starts off by faking his own credentials. That's really, really not a good way to start an interview with any kind of person at all. I suppose you could say that some media concerns let their journalists go undercover to uncover some certain things, but not like this. Let's start with some of the claims that he makes. The first one is about a book.
Also worth knowing is that in 1931, a book called 100 Authors Against Einstein was published in German, and is in the description. This shows 100 scientists stating Einstein was leading science into pseudo-mysticism, abstraction and speculation. It was crushed by mainstream science.
No, just like everything else here in science, things doesn't get crushed by mainstream science. It just so simply happens that as time went on, some of the predictions that Einstein made to sort of verify his own model, the general relativity model, they sort of came true. Like for instance, the shift in position of stars over the solar limb observed in 1919. Also the precession of Mercury, which had been observed prior to Einstein's model but couldn't be explained. And there are lots of other different observations that we have made that sort of verifies what Einstein said. So no, the problems with Einstein and this book wasn't that it got crushed, it was simply that it became completely irrelevant for the scientific community. And that is all. Let's continue.
Also know of the Dunning-Kruger effect, a cognitive bias in which experts mistakenly assess their cognitive ability as greater than it is. It's related to the cognitive bias of illusory superiority, and also comes from the inability of people to recognize these experts' lack of ability.
I'm sorry, but this is actually a bit funny. He is simply, he is verifying the Dunning-Kruger effect by stating that the Dunning-Kruger effect means something that it doesn't. Now let me tell you right now what the Dunning-Kruger effect means. The Dunning-Kruger effect is something that was observed that showed that uneducated or ignorant people with lack of knowledge in a certain area, had a tendency to sort of claim themselves to be expert in that given area. For example, flat earthers who bolsters themselves by having absolutely no education at all of any kind and still claim to be more expert knowledgeable than people who are actually educated within that field. Now, education in itself is not a guarantee that people know lots of stuff about different things, but it is a certainty that they should know more than the average person. As you can see here by the original article in the abstract, what it actually says. Let's continue on.
The first one I'm going to ask is, it is said that a spinning atmosphere has no border, there's no physical border between spinning atmosphere and the vacuum, and the atmosphere gets less pressured and becomes the vacuum of space. At what altitude would you say that the atmosphere stops spinning?
This shows a complete lack of understanding of why the atmosphere spins, what it does, and how it does it. So one of the important things to know or learn when you have to discuss the atmosphere and the Earth as a system is the conservation of momentum. In this case, the conservation of angular momentum or rotational momentum, if you will. What this means is simply that the atmosphere and the Earth was created at about the same time, something like that, or generated, whatever you want to call it. And that means that rotational velocity or momentum that the Earth had, the atmosphere had that as well. So asking when or where the particles in the atmosphere will stop rotating is a stupid way, sorry to say it, it's a stupid way to ask that question. Because the thing is that the particles don't stop rotating with the Earth, but there comes a time when other forces are more prominent than the rotational velocity, and it happens close to the Earth and also happens far away from the Earth. We have just recently learned that the atmosphere stretches itself all the way out to the moon. That doesn't mean that the moon has an atmosphere. It simply means that we have detected some of the particles that we can measure from the Earth, which are only present in the Earth's atmosphere, out around the area of the moon. They are still so scarcely filled up there. The density is so small that it doesn't really make any difference for the moon or the atmosphere in itself. So one other thing that people need to understand is that the rotation of the atmosphere is an average rotation. It means that on average, the atmosphere follows the Earth around. But as we have observed with satellites and by just looking at the skies, there's a lot of movement in the atmosphere because of the sun heats up the crust of the Earth and the atmosphere, and also because the rotation of the Earth itself, we have different movements. We have big circulation cells, the Hadley cell, for example, but then we have movements within those cells, partly because the rotation of the Earth, but also because the sun heats up certain areas of the Earth, the crust, and some other areas are cooled down because of lack of radiation. And that creates a very chaotic and dynamic circulation system that simply cannot just be explained by asking how much does the atmosphere rotate with the Earth. It's a complex system, but the atmosphere does rotate around with the Earth on average. And that average is very significant because that means that locally the wind can go in another direction than the rotation of the Earth. But if we were to stop the Earth right now, we would get gale force winds of up to 1,000 kilometers per hour. That's all the way around the Earth, because the atmosphere would have to have needed time to settle against the Earth, and that will create harsh environments for people to live in. So yeah, that's the reason why it's too simplistic to just ask such a question. Let's move on.
Like turbulence, what we call.
And the reason in mainstream astrophysics that the vacuum doesn't suck out the gas is because gravity is holding the gas to the Earth.
Yeah, exactly.
Because everywhere else in science, when there's a vacuum and gas, it equilibrates.
Yes. If you just take without gravity, yes, then they start to mix. Yes.
Okay.
Mm-hmm.
And that's absolutely correct. Now, the reason why I added this part here is because of that little video in the background where we saw this big container being crushed. And he sort of implies that why can gravity do such and such with the atmosphere and so on. So let me explain that. I have a little list here with points I want to explain. First of all, vacuum doesn't suck anything. And that's, I cannot really understand why people keep using that word, even though it is completely wrong. Vacuum doesn't suck anything or anywhere. I'm not sure whether it's because of the word the vacuum cleaner that people tend to think that vacuum should suck, but it doesn't. It really doesn't. So why does these things happen? Well, imagine all the air around the Earth, even though the Earth has a radius of 6,400 kilometers roughly, and the atmosphere is only 400 kilometers. Some say 100 kilometers. The part of the atmosphere that we usually tend to describe as the atmosphere is roughly 100 kilometers up. So it's a minuscule fraction of the size of the Earth. But nevertheless, the atmosphere does contain millions of tons of gas particles, oxygen, carbon dioxide, nitrogen oxide, all those things. And those things, because of gravity, has a weight. That is what generates the pressure on us, on Earth. That 1 atmosphere pressure is simply because all that air up, if you took sort of in physics, we usually try to simplify things. So we take we take a column of air, and then you could take all that column of air all the way up to the upper part of the atmosphere, roughly 100 kilometers up. Then you can calculate how much weight is there on the surface of the Earth, for example, from that entire column of air. If you take that container that they showed us in this little video here, and you evacuate that completely from air, imagine if you just take the column of air around that container and then all the way up to the top of the atmosphere, imagine the weight of all that air wanting to equalize itself with the vacuum inside the container. So that is why the vacuum inside the container doesn't suck anything inside the container. It is simply because there's lots and lots and lots of air wanting to equalize itself with that vacuum, that emptiness inside the container. That goes completely against and is the opposite of the astronaut in his spacesuit out in space. Because there you have the vacuum around him, and then he has this little container with air. And in that case, you have that tiny amount of air inside him wanting to equalize itself with the vacuum. But the difference is that there's not a lot of air wanting to escape. And the pressure difference is, just like here on Earth, only 1 atmosphere. So it's not so much about, so you could say that the real reason that container is crushed is because gravity. Not because gravity in itself crushes it, but because gravity pulls all that air down and makes it want to go inside the container to equalize it. It is a complete misunderstanding to say that vacuum sucks. Vacuum doesn't suck anything, and that is also why we can keep the atmosphere around the Earth without escaping into the atmosphere, even though some particles does escape. That's beside the point. The majority of the particles on Earth is locked to Earth because of gravity, and the vacuum around it doesn't want to suck it out. But if we were to cut off gravity, just like this, with a snap of a finger, that air, that atmosphere that we have here right now would almost instantly escape out into the vacuum of space. It would drift away because there was nothing to hold it against the Earth. And that also goes against some of the flat Earth arguments that we need a container around the Earth, the dome or whatever it is, in order to keep the air here. We don't. We just need gravity. Let's go on.
On to the next question. It is written in astrophysics that the rotation of the Earth is due to, we can't feel it because of constant velocity. Now, one astrophysics guy I met, he said there are two constant speeds. Let me show you this.
Yes.
A bit like this fairground ride.
Yes.
And some people I know looked at some rotation physics, and they said if you're on the edge of this, you would be experiencing acceleration and deceleration. It's only the middle point that would experience, like the wizard in the middle. The wizard would be constant velocity, but if you're on the edge, you get acceleration and deceleration because of the two constant speeds. How would you answer that?
Very simply, we have to consider that there are two forces at play here. Let's take away the idea of constant velocities and all that. Let's take the simple fact. We are on a rotating sphere. That means that we don't move around with constant velocity. We tend to use that as a simplification in order to explain lots of things because it makes our explanations much easier, and it also turns out that those simplifications can be justified if we compare them to the actual longer calculations. But in this case, it is actually a very simple calculation to look at. We need to consider two forces. One is the force of gravity. We have it here. The other, because we are accelerating, is the centrifugal force. Now, let me explain it like this. In an inertial reference frame, we don't have the centrifugal force. It is a fictitious force. We only have the centripetal force. And that's all. But what is an inertial frame of reference? Well, it is a frame of reference that is either stationary or moving with constant velocity. And since we are on a rotating sphere, we are not moving with constant velocity. This means that the Earth is actually not an inertial frame of reference. And that means that all those fictitious forces, the centrifugal force, the Coriolis force, and all those forces, they suddenly become very real and very observable. The Coriolis force, well, we can observe that by looking at the sky, at the cloud patterns, how they move around, the wind moving and all that jazz. But what about the centrifugal force? Well, I expect that one of the main arguments he's trying to make here is that because of the centrifugal force, we should feel the acceleration. Either whether he's talking about the Coriolis force or the centrifugal force, his argument seems to be that we should feel this acceleration. So let's look at the formula for the centrifugal force. We have it here. Alright, so let's take sort of a simple example. Let's take a human being with a mass of 75 kilograms. That means that his weight is roughly what we would call 75 kilograms or 750 Newton. We know that the radius of the Earth is 6.3, roughly 6.3 times 10 to the 6 meters. We can find the rotational velocity, the actual rotational velocity in radians per second by taking 2 pi, which is a circle in radians, and divide that by 86,400 seconds. That is the length of a day. And that gives us roughly 7 times 10 to the minus 5th radians per second. Let's take the first formula, the gravitational force. F equals m times g, where g is, let's just say it's 9.81 meters per second square in this case. It differs a little on the Earth, but whether we pick one or the other doesn't devaluate the example here. So if we take 75 kilograms and multiply that with 9.81 meters per second squared, we get a force of 735.8 newtons. Now, the key question is here, how much does that compare to the centrifugal force? Well, let's put in the numbers. Again, we have the mass of 75 kilograms. We multiply that with 7 times 10 to the 5th radians per second squared. That is entire 1 squared. And we multiply that with the radius of the Earth, which is 6.3 times 10 to the 6 meters. And we get 2.3 Newton. This actually explains us why we don't feel the rotation of the Earth. It's simply because the force of gravity is so much bigger on us, it's so much heavier on us than the force of the centrifugal force is. But of course, if we increase the rotation of the Earth, we would feel it, which is obviously what happened on a merry-go-round. We have a lot faster rotation in a lot smaller radius. Let's continue.
Wouldn't that mean we're not at a constant velocity, so humans should feel the rotation of the Earth?
I've just answered that. Yes, it does mean that we are not constant velocity, and no, we shouldn't feel it. Let's move on.
Yeah. In the 1700s, on the same theme, James Bradley did an experiment which was redone in 1871 by a G. Airy. Obviously, this is a long time ago. And also the Michelson-Morley experiment in 1887. All these detected no rotation of the Earth. It's a bit of a silly question.
They detected no ether.
No ether, yeah, I've read this.
Yes, no motion of the Earth with respect
to the sky.
And just like the astrophysicist correctly explained in the video, the Michelson-Morley experiment, which I cannot imagine why flat earthers keep pulling that out of their behinds without even checking the original paper. Alright, so now we have to take sort of a little physical history lesson. In the early times of physics, physicists knew that in order for sound to move around on Earth, it needed a medium. The medium was air, no sound. So it was reasonable to think at that time that in order for light to move around, it also needed a medium. But since they haven't observed any of the kind, they sort of invented the ether. Now, the theory of the ether, what the ether has to sort of rely on is that it has to be stationary with respect to anything else, because otherwise light wouldn't move as expected. If the ether was moving around, for example, with the Earth, we would have weird effects that could be observed. And since they weren't observed, it was reasonable to think that the ether had to be stationary with the entire universe for light to move around in it in the same manner. But then came the question, if we are, just as we know with the Doppler effect, if we are moving with respect to the medium that sound is traveling in, then we can hear a discernible difference. That is the Doppler effect. So how would that be related to the ether? Well, that is where Michelson and Morley came up with the idea to make an interferometer, one going in the same direction as the rotation of the Earth and one going perpendicular to that rotation. So the argument of the experiment was that if there was an ether, then as the Earth moved through that ether, we would see a difference in speed of light going in the same direction as the Earth, because as we travel through that ether, when we send out light going against the movement of the ether, the light would be slightly slower, and again on the turn back, it would be slightly faster. But that difference should be compared with that going perpendicular to the movement of the Earth, which should be constant all the way around. And so imagine that these two light rays, when they meet each other at that center point, they cancel each other. That's the idea of an interferometer. But if one is going at the same speed as always, and one is going slightly slower than it should be, then that interferometer would show a difference here. And also on the turn back, this would be going faster than normal, but this would go at a normal speed. There would also be a difference, and that would be shown in the interferometer as interference. But Michelson and Morley didn't observe that, so their conclusion was that there could be no either. And so along came Einstein and actually made the either non-necessary. So that's the explanation. But flat earthers keep wanting to introduce this experiment to show that the earth is not moving, even though they don't have an experiment to verify the either. They, just like they did in the 17th and 18th century, just had to imply that the either was there. Let's move on.
What scientific method, instrumentation, or experiment would you say proves the Earth is rotating? What would be your first, number one best proof if you were doing a lecture?
Let's get this clear once and for all. Science doesn't prove. Science examines, science verifies, and science tries to figure out what is the most plausible explanation, but science doesn't prove anything. But besides that, what would I take as my first argument to say to people that the Earth is definitely rotating? Well, I would take a combination of observations. I would first look at how the stars move around on the sky differently depending on your latitude. So, for instance, here at the northern hemisphere, the stars seem to go up at some point and down at some point. If you are at the equator, the stars seem to go directly up at the west and set in the east. And if you're either of the poles, the stars just seem to rotate all around you all the time. That certainly is very consistent with how you would observe things if you were standing on a rotating sphere. If we combine that with the parallax of the stars, then we can certainly ascertain that the Earth itself is also moving in some sense, because if the stars were completely fixed above us, we definitely wouldn't see a parallax. So that would be my two number go arguments and also experiments that can be performed by anyone.
Let's go on to gravity. This is probably come across as a very obscure question. So these people said to me, gravity is strong enough to hold boats and cargo and cars to a spinning ball, but yet it's not strong enough to pull the butterfly down or these small areas of these dead flowers. How would you answer that?
Oh, how would I answer that? All right. First of all, as I've just shown, let me get it again. Here is the formula for the gravitational force. If you flat earthers want to discuss the physical understanding of gravity, you need to use this formula and you need to understand it. You can't just invent your own truth and then say, well, gravity is false. No, because that's not what gravity says. So let's take it once and for all. Gravity pulls, well, if we stick to the Newtonian understanding of gravity, which is admittedly wrong, Einstein is correct. But nevertheless, the Newtonian law still works, and let's just stick with those and just use this interchangeably, that Newtonian understanding of gravity is somewhat accurate. It's not accurate enough, but it's somewhat accurate. It can hold up to scrutiny at certain points, and it certainly makes the understanding of what I'm going to say much easier to understand. So let me try to explain what gravity says, what gravity is, and our current understanding of gravity. Now, if we want to flat earthers has a tendency to try to put Newtonian out on a sideline because he was wrong. And yes, admittedly, he was wrong. So let me say it in an Einsteinian sense. Anything and everything in the universe with mass will move and bend the space-time around us. And just to be clear, it is not space and time, it is space-time. It is one entity in 4 dimensions, 3 spatial dimensions and 1 time dimension. That bending of space-time will then again tell any particle, also those without mass, how to move around. So essentially you can say that gravity will attract anything with mass. That's a reasonable simplification of the understanding. Gravity, as you can see from the formula, is also dependent on mass. The more mass you have, the greater gravitational pull. Now the oceans, as far as I know, have a pretty big mass. They are pretty heavy. Well, heavy because gravity pulls in them, but they have a pretty big mass. Lots of mass. A butterfly, it has a relatively little mass, small mass. That means that gravity pulls much less in the butterfly than it does in the ocean. As far as I'm concerned, that makes perfect sense. But I can assure you this. If you, depending on how sadistic you are, but let's make a thought experiment. If you took a random butterfly and clipped off its wings and then dropped it, it would fall to the earth. So the reason why a butterfly can fly is because it has wings to generate an upward force that is greater than the gravitational pull. Because the butterfly is very light, it will fly. But again, if you take a little string and you put it around the butterfly, you strap the butterfly to a big 4 kilogram weight, the butterfly will not fly anywhere. I guarantee it. So because the combination of the butterfly's little mass and the wings that it can flap around to generate a force with, it can fly. Now the little thing is that he also mentions from the flower, it's basically the same. Because they are very light and they have a big surface area at the top. You can see that those little feather thingies sticking out, that's a big surface area. So when the wind comes, it can grab on to, if you will use that word, the surface area can use the force generated by the wind to move itself up and away. But when that force is gone, it will slowly drift down to the ground again. So gravity pulls in everything, and there is a completely logical explanation why birds and butterflies and these little things from the plants can fly and all those things. There's also a perfectly good explanation why I can't fly. But if I strap a rocket to my back and turn it on, I will fly, because then the rocket generates a force that is greater than the gravitational pull in me. But if I take a little New Year's rocket, well, that won't happen, because that can't generate a force big enough to fly me away to the moon. Let's move on to one of the main subjects of this scientist here, that he also asks about.
And move on to your subject, exoplanets. What percentage surety do you have of there being other Earth-like planets? Are you 100%, or are you 80%? Or are you 65, or do you change each week?
Well, first of all, that's again a ridiculous question to ask. We are talking about certainties. Certainties can change. If we have very good data, we can get a high amount of certainty. If we have very unsecure data, we can get a low amount of certainty. So yes, the certainties will change. Regarding the question how certain we are that there are exoplanets around in the universe, in the galaxy that we can observe, we are pretty certain, because we observed a lot of them using different methods. We can see that there are objects revolving around these stars, and they have certain elements in their atmospheres because we can see it in their spectra. Let's go on to his next. He has a lot of I think it's a sub-question or something like that.
With these people I was speaking to, let's pick the TRAPPIST-1 system, the one that got into the media. This was the image, and I believe with photomy and other ways of measuring, I think you measure the brightness, the electromagnetic spectrum, and spectral changes. Then this turned into this colourful planets with volcanic activity, water content. How do changes in electromagnetic activity and spectral activity and brightness, such as the image in the bottom left, how does this turn into all this information about volcanoes and water and size and atmosphere?
It doesn't. That's the simple question. It doesn't. What scientists can do What astrophysicists can do is that we can take these images of the star by using the occlusion method, where the object goes in front of the star, then dims the light. He also shows that in the video. And then when the occlusion is gone, the intensity goes up again. We can use that to estimate the mass of the object revolving around that star. If we combine that with the spectra, where we can see sort of the composition of that atmosphere around that planet, we can say certain things. If there's a lot of carbon dioxide in the atmosphere, it is relatively certain that there must be some kind of volcanic activity. And also, if we can find a lot of water in the atmosphere, it would also seem reasonable to think that that planet has water on it, either in the atmosphere alone, but probably also on the surface. Now, also, depending on where it is in relation to the star it revolves around and all those things, we can actually say a lot about that object. But those pictures that he shows are interpretations by artists. So what artists get, they get a lot of information from the astrophysicist regarding the content of the atmosphere, how much water, how much carbon dioxide, all those things. They get sort of a rough explanation of how that planet might be. And then they use that knowledge to interpret how they think that planet would look like if we could sort of be relatively close to it. But it's not a scientific piece of data. It's an artist's impression. And that is something flat earthers seem to struggle very much with. Either way, whether it being images of the Earth or images of exoplanets. Let's move on.
I have a couple of questions about the moon. I'm sure this is just an error with NASA. This is a famous image called Earthrise.
Yeah.
If you put on a lens with a very wide area, wide lens on your camera, and snap an image of the Earth from the moon, that Earth will look very small. If you, on the other hand, take a lens with a very small field of area, like a zoom lens, and zoom all the way in on the moon, then the moon will look very big. If you do the opposite, then the moon will look very small and the Earth will look very big. So these two images, it's just like comparing apples and oranges. Because an apple is smaller than an orange, then there must be something wrong with both of them. No, there isn't. It's simply a matter of the kind of optics that you use. Let me give you an example, again with these apples and oranges. Let me take an image of an apple where I use a lens with a very narrow field of view. That apple will look incredibly big. Then I take an image of a basketball at the same distance, but using a lens with a very wide field of view. Then that basketball will look very small, smaller than the apple, on that same image, that same size. That doesn't mean that the apple is just suddenly bigger than the basketball. It's simply a matter of the kind of optics that you use. But I will say this, if a flat earther can find an image of Earth from the moon and then find out what kind of optics, what kind of camera size, all that field of view was used, and then compare that apples to apples with a camera using the same field of view here on Earth, and find that there is a big discrepancy of the sizes, then I can argue that we have a problem. But just taking two images and comparing them, that doesn't make any sense at all. Not without knowing the field of view of the camera and all that. Let's continue.
This is interesting. Some people I know were measuring the moon. They're interested in space and the sky. The moon was photographed at the same time in Australia and Florida. How would that be possible? How's that possible?
Well, it is perfectly plausible and possible because the Earth is a sphere and the moon is revolving around the Earth at a big distance. Now imagine my hand here is the Earth, if you can see it. And this hand out here, my little finger here, is the moon. If I have one person standing here looking at the moon, and I have another person here standing down here looking at the moon, they can both see the moon at certain given times. But why not just settle for my word? Let's take a program like Stellarium. Now, I hope we can all agree that Stellarium is a program that is based on the heliocentric model with a rotating Earth and all that yada 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 yada. If you put in the data that he has presented here, and one of the things that I got a little suspicious about his example here is that he first of all takes Tennessee, USA. Tennessee is a state. Sydney is a city. So comparing a state to a city, well, that's not really useful, right? And also he compares the state of Queensland with the state of Florida. That is also very imprecise. But nevertheless, I try to put in certain cities and certain areas in Stellarium at certain dates. And as you can see on the image here, it holds up to scrutiny. You can actually, using the heliocentric model, see the sun at different times, both in Tennessee and Sydney, and also in Queensland and Florida. So yes, it is both perfectly explainable using the heliocentric model, but it is also perfectly plausible. Let's move on.
Okay, with the moon, it does this other strange thing. On a solar eclipse, you know, where
Yes.
coincidentally the sun and moon appear the same size, which we're saying is a coincidence, yeah? The moon does a shadow on the Earth, yeah? Now this shadow is 100 miles wide.
Yeah.
This is the only phenomena in our experience here in this reality where the shade is smaller than the object casting it.
No, it is not. Actually, you can show for yourself that whenever you have a source of light that is larger than the object casting the shadow, there will be two distinct shadows. There will be the umbra, which is the actual shadow, and then there will be the penumbra, which is the sort of the outer shadow, the lesser shadow, and that is because the light from that light source is coming all the way around, just not the corners, and they are hitting all the way around on the object, not just the ends. So that means that there are at least 4 lines that you need to account for in order to explain where the shadows will be. And you can draw that yourself. Take a big object, that's the light source. Take a smaller object, that's this object casting the shadow. Take a wall at a certain distance and then just draw lines all the way around. You will get an umbra and you'll get a penumbra. Now, the shadow that he's talking about is the penumbra, and that is definitely bigger than the object itself. And it is at least the same size as the object, as the same size as the moon. But the umbra itself is smaller, and that is because the light source that we are using here, the sun, is incredible much larger than the moon itself. So it is perfectly plausible and also perfectly explainable, and you can test that for yourself. Take a huge source of light, take a small object, and then try to cast shadows and see what happens. I might do those kind of experiments just to show you that it is completely plausible. Let's move on.
This is a quick question a friend wanted me to put in. He said, with the lunar lander, there's one rocket. How would that land with one rocket when the spacecraft is asymmetric? Like, we haven't seen on Earth a craft landing. I mean, the SpaceX one, they say lands, but that's very symmetrical. So it's a very asymmetric lunar lander.
Yes.
Surely we'd have seen that being tested on Earth, or
Yes,
we'd see
yes.
things now.
It's jumping. Yes.
Well, first of all, there were more than one rocket on that lunar lander. Just like on just about any other rocket, and also the command module and all those different kind of objects that we have put into space, there are main boosters. Those are responsible for generating a lot of thrust so that a rocket can get out into space, it can land again, and also so that the lunar lander just doesn't crash down into the moon. But then there's also the rocket system, the RCS system, I think they're called reactor control systems or something like that. They spew out a little amount of energy, just enough to move the lunar lander a little bit around. So you have to, it was a feat, no doubt about that. So imagine that you're using this booster when you go toward the moon in order to slow you down. Now, please remember that the gravity on the moon is much less than the gravity on Earth, and also you don't have to compete with the atmosphere. But nevertheless, you have this lander going down towards the surface of the moon. And then imagine that you're tipping it. You're trying to balance it on a tip, and you're using those reactor rockets to sort of shift it around so that it doesn't just tumble around and crash into the moon. So I can assure you that whoever landed that lunar lander, he had a lot of work to do to keep it balanced, but that is not the same as saying that it is not possible. And that is definitely also not the same as saying that they only had one rocket. They had couple of probably 4 or 6 or 8 or something like that of these reactor rockets spread all the way around in order to shift it around. Let's go on.
And they had when the lunar lander took off, they filmed it. You know that piece of footage? The lunar lander takes off from the moon and they created a film. It was like a 10-second film of it taking off. Mm.
Yes, and so what's the problem with that? As far as I know, television at that point could be transmitted using radio waves. So I can't really understand why it shouldn't be possible for an automatic camera to follow the lunar lander up and also send those video data to the lunar lander using RF waves. I can't see why that should be impossible. But nevertheless, it was done.
I as an independent journalist, I can't use pictures as evidence.
Oh, you as an independent journalist cannot use pictures as evidence. Well, I want to ask you this. What is the difference between data and an image? Let's take an example. I take a CMOS chip and I put it into an instrument and I slap it onto my telescope and I put in a filter in front and I take data. I get photons through that filter. I then take that same chip, that same CMOS chip, and put a biomatrix in front of it and put it into a phone, and I take an image of it. Why is one data and the other is not? I think that's a question that you flat earthers should think a little bit about. Also, why you claim that you can get accurate results using the P900, which definitely has a biomatrix in front of it, while images taken with the Discover satellite and the EPIC instrument, where they shift the filters out so they have red, green, blue and all different kind of filters and combine them, those are not real. That is also a question for you. But let's move on to the next point.
Going on to something a bit interesting here. This is recognized all around the world as the spherical trigonometry of the curvature of the Earth, yeah? Mm.
Yeah, and why do you use that? Because you can't really use it for anything, especially not the argument that you're trying to make. Let's go on.
So, do you prefer kilometers or miles?
I prefer kilometers.
Okay. So, if we were to look, let's try and make this brighter. Mm-hmm. If we were to look 50 kilometers, there should be 195 meters below the curvature.
Yes, there should, if your head was buried just right along the surface of the Earth. But if the observer has any kind of height with respect to the surface of the Earth, that calculation is completely and utterly useless, which is also directly implied in the argument that you're trying to make next. So again, why in the world do you include this in this discussion?
What if I told you I knew some people who over 4 years have done about 50 to 100 experiments, mm-hmm. and they can see lighthouses and have done laser tests over between 30 and 60 miles. So like a laser hits a mirror across a long lake, like Lake Constance, mm-hmm. Near Constance, near mm-hmm. here. and seeing things like Chicago's skyline from across Lake Michigan from 50 miles away. And they factored in the height of the person and all the maths, and that these people actually cannot find the Earth's curvature.
Well, first of all, the curvature of the Earth, well, using a laser, did they account for the divergence of the light cone from that laser? Because at a distance of 30 to 50 miles, that laser cone will be pretty big. And even if you say that roughly halfway along there, the curvature should be at the highest, and so part of it should be obscured, I'm pretty sure that cone would be pretty big, and part of that light will shine over the curvature of the Earth because of that divergence of the light cone. So that might be an explanation why they can see a laser across the surface of the Earth. Also, did they account for the diffraction in the atmosphere of that light? For instance, lighthouses can be seen very far away because of that diffraction of light. Regarding the Chicago skyline, well, that has been shown many times to be related to diffraction in the atmosphere and what we tend to call inferior and superior mirages. I can't really figure out why flat earthers tend to use that same false argument. Let's move on and see what comes next.
To have
This is a test, a scientific test.
who did on the horizon?
I could show you with this camera ships, they go over the curvature. I could show you them coming back.
No, you can't. You can't show ships going over the curvature and coming back. What you can show is that when you zoom out with whichever camera you're using, probably the P900, I don't know why a P900 should have so big a difference and such good optical elements, but nevertheless, that is the flat earther's favorite instrument, and let's stick to that. It's probably a P900. In that P900, every optical setting that you can use, every zoom setting, every time you change the field of view, you also change the angular resolution of the camera. So what you show here is that when you use a wide field of view, low zoom, whatever you want to call it, that camera has a very low angular resolution. And what you're trying to look at, that little ship that you says go over the curvature and comes back, that resolution, that angular size of that ship is less than the resolution of the camera. And then when you zoom into the ship, you change the angular resolution to be larger than the angular size of that ship, and then lo and behold, you can see it again. But I assure you this, if you take a telescope, which has a really big angular resolution, you slap that onto the beach and you follow a ship, at some point that ship will be gone. And if you calculate how far away that ship should be in order to have that angular resolution be the problem, this ship should probably be somewhere around the moon or something like that. So I don't think that the ship will go that far away, honestly. It's the same problem that flat earthers has with the sun. The reason why we cannot see the sun at a certain point, the reason why the sun sets, is simply because it becomes too small for our eyes to see it, which makes it a bit hard to understand why we can see the stars. But nevertheless, if you calculate it, which I've done here, you can see that if you assume that the Earth is flat, it has a certain size because we know the distance from the North Pole to the South Pole. We do that because we have measured it. If we then calculate how far away should the sun be, giving that size here, which flat earthers tend to claim it has, it should be lot farther away than the size of the Earth itself. That doesn't make sense at all. So the real explanation why you can get that ship back into the camera again so you can see it is because you changed the field of view. You changed the angular resolution of the camera, and lo and behold, things will come back when you do that, because if they are smaller than the angular resolution and then again become larger than the angular resolution, you will see them again. It makes perfect sense if you just know a little bit about optics. Alright, that was it. That was all I had to say about Flat Earth in this round here. I will be back again, probably, I think, with more videos. I have to go through all those misunderstandings and misinterpretations that Flat Earthers use, and then I will see you again. As always, if you like this video, give it a thumbs up. And if you really like my videos, then subscribe to my channel, and then you'll get notifications whenever I put out something new. See you in the next video. Bye bye.